Hi, I'm Dr. Matthew Michal. I'm a lecturer of mathematics at NJIT here in Newark, New Jersey. I've been talking about differential equations, specifically the Boyson-DePrima 10th edition. I'm trying to give an idea of review of concepts. These are their lecture notes, and so I'm working through and kind of explaining what the heck is going on. Okay, so chapter 3 so far has been all these variations of how to deal with homogeneous and then the non-homogeneous, basically solving and working through the different steps of solving a second-order differential equation. So now let's take a look at how this might be seen in an application. So we did mathematical modeling in chapter 2. This is mathematical modeling for chapter 3. How does a second-order system model a real-world scenario? The two that you see most often are what you see down below, or the one that we're going to use. The one that's a lot in differential equation textbooks is this spring, a mass on a spring. Another good example is circuits. Circuits are used a lot in different second-order systems. There are others as well, but these two I see a lot as a mathematician. So, the spring mass system. So let's say we have a spring. This spring has a mass m, which hangs from a spring which originally had a length L. However, when I put the mass on it, it's going to naturally stretch the spring according to Hooke's law. Since I'm stretching the spring an extra capital L length, L for length of course, the spring will stretch according to Hooke's law of KL, the force of KL, Hooke's law. And gravity is pulling it down with mg. So once it reaches equilibrium, that mg should equal to KL because the force due to gravity is canceling out with the force due to the spring. However, I'm interested in motion. So after it is stabilized, then I pull on it with some initial displacement and initial velocity from the equilibrium position. This displacement is going to be described as an extra u from that central place. So you could be positive, a little extra pull, a little extra stretch, or you could be negative, i.e. it's a little bit above the equilibrium position. So notice positive is going to be forcing it down based on the stretch. The stretching was a positive stretch. Okay, so according to Newton's second law, we have force is equal to mass times acceleration, or mu double prime is equal to f of t. So we have different forces going on that we need to consider. Weight, that's m times g, mass times the acceleration due to gravity. Spring force, remember we now have a an extra little bit of displacement u, so instead of it just being k times L, it is KL plus u. K times the sum, L plus u. Now also notice now we're considering Fs to be negative, because where weight is wanting to pull it down, force due to a spring is wanting to move it in the negative of the displacement. It wants to move it up or away, whatever's going on. Damping force wants to slow it down. So damping force is saying, hey, look, I'm moving. So negative, let's slow it down, hence the negative. And any external forces, which might also occur, we're going to call F of t. That's going to be our forcing. So here, kind of what we're talking about with spring force. Spring force is K times the sum L plus U. Explaining why we have that negative sign. Here's the damping force kind of ideas, talking about if U prime is positive, i.e. it's U is increasing, then the mass is moving downward, which means I want to slow it down, so we have a negative value, and vice versa. Gamma is just going to be the strength of that damping. But it'll always be positive because we're not pushing it along, we're trying to slow it down. So gamma will be positive. So putting it all together, MA, or MU double prime, is equal to mg plus the spring force plus the damping force plus the external forcing F of t, which this could be anything from like a machine pulling and pushing. It could be a cat playing with it as if it was a toy. It could be anything. This is any other external forces we haven't accounted for yet. Putting all the U terms together and realizing that, remember, mg cancels out with KL, so mg minus KL cancels out, and we're left with a second order equation of the form A U double prime plus B U prime plus C U is equal to some forcing term G of T, or in this case F of T. So its initial displacement will be U prime, its initial velocity V naught, which is U prime of 0. According to theorem 3.2.1, since M, gamma, and K are continuous, actually, after all, they are constants. As long as F of t is a continuous function, we're going to have a unique answer. So let's look at some of these examples, right? So we have a 4-pound mass. That's imperial measurement system, not metric, so that's annoying. A 4-pound mass stretches a spring of 2 inches. Spring 2 inches. The mass is displaced an additional 6 inches and then released. Release sounds like we have a velocity equal to 0, initial velocity, and is in a medium that exerts a viscous resistance of 6 pounds when mass has a velocity of 3 feet per second. I want to formulate an initial value problem that governs the motion of the mass. Okay, so mass, that's gonna be a little bit, you need to be careful because 4 pounds is a weight, not a mass. So 4 pounds divided by the acceleration due to gravity. In imperial measurement systems, that's 32. So my mass is going to be 1/8 pound. Well, 1/8 pound second squared over a foot. That's what happens when we use imperial measurement systems. Gamma, that damping force. Remember gamma U prime, that the forcing is 6 pounds. Remember, it's 6 pounds of resistance divided by the speed U prime, so that's 3 feet, so that's gamma is equal to 2. K, that is going to be how far does it stretch when I apply a certain amount of force. So in that case, it stretches 2 inches when I apply 4 pounds. That's the first sentence. So we don't want this in terms of inches, we want this in terms of feet. So that's going to be 4 divided by 1/6 foot, or feet. That's 4 times 6, or 24. Remember how I said how that being released, that's a half. Released, so that means it has no initial velocity. And since it was displaced an extra 6 inches, that's a half a foot. Okay? So that means 1/8, that's m, 2 was gamma, and k was 24. Let's get rid of that 1/8, so multiply everything by 8. I'm going to get u double prime plus 16u prime plus 192u is equal to 0, with initial conditions of an initial displacement of 1/2 and an initial velocity of 0. Okay, so using the quadratic formula or completing the square, we can get a solution of the bottom type, right? Because we've already done this before. The hard part is setting it up. Now that we know how to solve these, this would be just something straight out of a complex root. We can just imagine what's going on. Okay, one last thing before I continue on. We might need to be able to sketch these, so let me talk through this briefly. Initial displacement of 1/2 means it has a positive y value or a positive u value of 1/2, hence this 0.5. U prime is equal to 0 means that it starts off with a flat slope. And since e to negative 8t, that means it's shrinking in size, even though cosine and sine are oscillating. So we just start wiggling around the 0. That is shrinking very, very fast. Oh, that's because it's negative 8. Duh. Okay. So, general form m u double prime plus gamma mu prime plus ku is equal to f of t will always be our kind of concept that we're building off of. So if we have an undamped system, we make gamma equal to 0, and if it's a free vibration, that means there's no external driving force, so that means f is equal to 0. And we get general solutions. Remember, m, you can't have negative mass. Well, I don't think so. Talked to a physicist. And a spring constant is k, is going to be positive. So that means we're going to get a purely imaginary root where that frequency, omega naught squared, k over m, that's the natural frequency of vibration. So some clever trig identities. I think this is the reduction formula, if you remember. So once we get our solution in terms of a cosine omega naught t plus b sine omega naught t, we can reduce it down to a single amplitude problem, r cosine omega naught t minus delta. R is going to be, if you notice, the square root of a squared plus b squared. So once I determine what my coefficients are from the initial conditions, I can simplify it down to a single cosine term using the reduction formula, which is kind of built off of the sum difference formula for cosine. Also, notice this omega naught was from k over m, right? So our purely imaginary root, that tells us how fast this is vibrating, the natural frequency. And remember, periods, the period of vibration, that's 2 pi divided by omega naught. So we can make a couple of observations that the bigger the mass is, the longer it takes to vibrate. So that's a smaller frequency and a larger period of time. K is talking about, if you remember, the spring strength, that spring constant. So the stiffer or the stronger K is, the faster it's going to vibrate, which makes sense because an undamped free vibration problem could be described as your voice. And if you talk about pitch, oftentimes we have hugely high cases for pitch. Your vocal cords are very stiff springs, as it were. So that's why when you talk about pitch, like in an orchestra, concert A is at 440 hertz, whereas our vibrations of a spring, which isn't quite as stiff as our vocal cords, has a much lower frequency. One other thing to recognize is that delta is going to be describing the phase or phase angle of what we're doing. It's what kind of shift is required for the cosine for it to occur where it is. R is, of course, the amplitude. How big are the bounds of my vibration? Okay, let's do this again. A 10-pound mass stretches a spring 2 inches. The mass is displaced by an additional 2 inches and then set into motion with initial upward velocity of 1 foot per second. Remember, upward means negative. Determine the position of mass at any later time and find period, amplitude, and phase of motion. Notice we have no talk of gamma, so that we have a gamma is equal to 0, unless it says otherwise, which in this case it doesn't. So we're going to, so mass, because notice that's 10-pound mass, so 10 divided by 32, that's 5/16. Yeah, because that's friendly. And then we find K from the spring force. Well, that was a 10-pound mass, and it stretched. It stretches the spring 2 inches, right? So that's 10 pounds divided by 2 inches, or 10 divided by 1/6, or 60. So that extra displacement, that gives me an extra, that's my initial position, is 2 inches, or 1/6 of a foot, and an initial velocity of an upward or negative 1 foot per second. So I have 5/16 u double prime plus 60 u is equal to 0. So if I divide by 5, that'd be 1/16 u double prime plus 12u. And then if I multiply it by 16, well, 12 times 16 is 192. So that number keeps coming back. Well, if you remember, we always get this from dividing k divided by m. So omega naught squared is k divided by m. So the square root of 192 is going to be our frequency. Plugging in our initial conditions, this is what we end up getting. Notice you can pull out a 64 from here. Notice this, you divide it by 3, you'll get 64. So we can simplify our lives and make this a little bit nicer to look at. Natural frequency is not going to be anything pretty to look at, so we like to leave it as 8 square root of 3. The period, if you really want to, is this. Amplitude in this case, I'm going to take square root of 1 over 36 plus 1 over 192 in order to get this number. That's not necessarily anything beautiful, but the amplitude is about this size. So that's why our bounds are between negative 0.2, and positive 0.2. It doesn't quite reach all the way there. You can see all this kind of working together. So that I could write this as follows. The 0.182 cosine of 8 square root of 3p plus my phase angle here, because this is a negative answer right here. So, we've talked about complex roots, we've talked about real and distinct roots, we've talked about repeated roots. What does this mean in the context of a problem? What is the application? What does this mean? Well, we talked briefly about undamped motion. That's something that never stops moving, hence a voice or sound. But we have these three cases. Once again, we have the discriminant here that we're going to consider. When gamma squared is bigger, when gamma squared is smaller, when gamma squared is equal. Remember, when gamma squared is greater than, we get real and distinct roots. So this is saying when remember, because gamma is referring to friction or resistance, when I have a strong enough resistance, that means I get real and distinct roots, which makes sense, because if I have really strong resistance, like if I put my spring in molasses, yeah, that's not going to be a lot of vibrations inside that honey or molasses. It will return to equilibrium position eventually, but it's not going to do a whole lot of vibrating. If I don't have a lot of resistance, if it's just a little, notice we get my vibration cosine and sine, but there is a bit of a decay going on, because friction does have an effect. I mean, if you push on a swing, it doesn't swing forever. It eventually stops moving. So when the friction isn't very much, we get a vibration, but a slowly decaying vibration. And lastly, when gamma squared is exactly equal to 4mk, when the friction equals the effects of the mass and the spring constant, we get what's known as a critically damped case. We get a case where it is exponential, but we have repeated roots. So there's that small damping that I just was talking about here. So it's decaying in size, but it is vibrating. We have, and in that right there, there's an important concept that vibration mu is not quite a frequency, because note, it's not going all the way up. You know, this trough and this trough aren't quite lined up the way it should. So we call it a quasi-frequency because it is vibrating. It's not quite vibrating all the way. It's not quite making it all the way there. So it's a quasi-frequency because it's close, but it's not quite a frequency. We can take a look at their ratios to see how they compare. This isn't a big thing, but we can approximate it because we're assuming there isn't a lot of resistance. Otherwise, why are we vibrating at all? So 1 minus gamma squared over 8 km is a good estimator of how much of a resistance, what is the frequency as compared to the quasi-frequency is compared to the natural frequency, the undamped motion. Notice if I have no resistance, gamma is equal to 0, I get a ratio of 1. They're exactly equal to each other. But as I get closer and closer to that, notice that as I add more and more frequency, more and more resistance, mu is getting smaller and smaller. It's the opposite effect for the quasi-period, the period of the quasi-frequency, if you will, because the less it vibrates, the longer between vibrations, which means a longer period. Hence the plus rather than the minus. Critical damping is the case where they're exactly equal to each other. If gamma is too big, we typically call it overdamped, whereas gamma that's small is underdamped. Critical in mathematics means that it's a special place. It's transitioning from under to over damped. That's all we're referring to here, and that's why we have repeated roots, because something interesting is happening at that point. So we get these interesting exponentials that have a maximum in an interesting place. That's why you notice the red and black graph, which are critically damped, have the max and min, whereas the green graph, which is just a overdamped system, goes straight to 0, and the underdamped vibrates, and that's blue. So here's an example of what you might see from an underdamped problem, because notice there is a gamma term. We have an initial extra displacement of 2 feet, 2 meters, whatever, initial velocity of 0. We can solve this, and we get a quasi-frequency of square root of 255 over 16. We can solve for the amplitude r by taking the square root of 4 plus 4 over 255. And so we get 32 over the square root of 255. We get a phase of 0.06254. That's not so much as important. A lot of times it's good enough to just say delta is equal to the arctangent of this ratio. Notice that if this damping term wasn't there, I'd have u double prime plus u is equal to 0. That's why we have this omega naught equal to 1, and its period being 2 pi. And we can actually compare the effects of these two. The undamped case in the dashed line here, and the damped case in the blue here. So notice the blue does fit inside the undamped motions path, but it's shrinking in size, unlike the undamped, which keeps the same size. Also, we can use Mathematica or MATLAB or some kind of solver to predict at what point does that vibration not really matter anymore. So this is a case where we were looking to see at what point does it vibrate less than 1/10 of a foot, or less than 1/10 of an inch, or 1/10 of a meter. At this point, it doesn't really matter. It's vibrating very, very little. And that time turns out to be 47.515 seconds. So just a little bit less than a minute. Electrical currents is the other case. This basically follows from Kirchhoff's laws. And so what we do is we focus on the effects of where the voltage drops. Because we have inductance, we have impressed voltage due to a battery or whatnot. We have resistance across the resistor, and capacitance. So if I remember right, Li double prime that is from the, this is from the inductor, this is from the resistor, this is from the capacitor, and this is coming from the battery or whatever this inductor crest voltage is here. And so we can also do this both with current as well as with charge. So remember that current is the derivative of charge because current is how fast something is flowing. So your book does a really good job. Boyce and Prima does a really good job of explaining what this is. Like it says here, more details, see the text, but that's basically what's happening. You're just doing the same thing with the spring, but now with the circuit. Add up all the voltage drops together, create one giant equation. Have a great day.